Hi, this is Traxi Computer Science, and today we're looking at part 3, which is distributed and parallel computing. Last week we discussed how the performance on a one machine was impacted with all the layers. Now, this week we are discussing many why distributing work creates a compute problem for a coordination problem or a communication problem. So, does always add machines provide the right answer? And to just set the context, whenever we hit a compute or a memory problem, all of this engineering teams typically just say, hey, why don't we just add more machines? And if we are not experienced enough, we know that's a, though definitely not a lie, but limited in the options that we have. So the idea is that, hey, distributing work creates a compute problem for a coordination problem, because now you have the same kind of work happening through multiple machines, and while they are working faster, but the machines also now need to talk to each other, and past a particular point the communication becomes very limited in nature because it's passing through network and so on. And that trade has a name. It is called the communication bottleneck. Yeah, it governs the GPU cluster economics. How much network bandwidth are we using, how much communication is happening, and so on. Yeah, and the price of frontier models also depend on that, and whether we distribute it is actually faster or just pricier is the question that we are talking about. Yeah, does the system really get faster, or we just made it more costlier? That's the question that we are trying to answer. Yeah, and PM's job is, we need to understand when this distribution is forced or it's premature, and we need to be that person to show the math or propose the math before we go ahead with the decision. And this week's drill will be that we need to talk to our engineering teams, challenge a, hey, we need distributing training proposal with the scaling math. May not be training, if at least on how much compute are we using for our features or products, and is that optimally calculated and provisioned. So this is the session roadmap that where we're going to go through. We understand why distribute in the first place, what are the two forcing functions, and how these forcing functions probe us on why distribute is important in the first place. We'll understand the difference between parallelism and distribution. Yeah, what does parallelism mean? Executing a task in parallel versus distributing a task. We are gonna also look at one brutal law called Amdahl's. Amdahl's tells us that the more you try to distribute the work, that there is a limit that we are going to hit, and beyond that we will never see performance improvements across a distributed network. And there are challenges with distribution as well. For example, cap, the consistency, availability, and performance related positioning. Yeah, so how do we handle for consistency and partial failures in distributed networks? We're also going to look at, hey, how does distributed training happen, the data, the model, the pipeline parallelism, how it is built. One thing then we are also going to look at is the communication bottleneck. Yeah, and why the money is flowing into that bottleneck. Finally, we'll pressure test a distributed proposal that our engineering team says. So why distribute and why not? Yeah, we are somehow going to pay the distribution tax when one machine genuinely can't do the job or task. So why distribute it in the first place? Typically it arises from 2 points. Yeah, two forcing functions uh, ask us, hey, go and distribute the data, sorry, the task. One, when it is memory bound, I do not have enough memory to store all the weights of a training model. Yeah, imagine a 400 billion parameter model which needs hundreds of GBs. We just noticed last time that along with the weights, if you had to hold additional gradients and all to train, it requires at least 800 gigabits of memory, at least twice the billions of parameters. Yeah, 400 billion would need at least 800 gigabits of memory. A single GPU does not have that much, so we must split it, and this is not optional. But if it is too slow, if it is compute bound, we could always say that, hey, trillions of tokens on one GPU would take years. Why don't we split it, the task, into weeks? We can reduce the scope, we can reduce the data that is needed for training and so on. So while it takes some time to compute, it is only slow. Yeah, it doesn't say, hey, go and have multiple machines. So sometimes this has a single machine answer. If the compute is slow, increase the size of the machine, that could solve the problem. So the discipline that we need to follow is, hey, we need to name the forcing function which is forcing us to go for a distributed network. Yeah, before we design anything. Too slow means it has a single machine fix. We can go for a bigger GPU, a better algorithm, or less data. We can solve for any of that. But doesn't fit with respect to the memory. It requires splitting the system or distributing the data into multiple things, whether we like it or not. And the difference between parallelism versus distribution is pretty simple. Parallelism is doing many things at once in parallel, concurrently, and multiple cores or GPUs in one machine are running and they all share a memory. But in distribution, multiple machines are there and it is the work is shared over a network, and it does not have a shared memory. Here in parallelism it has shared memory, here there is no shared memory. So they must send messages separately to individual machines, collect them back, and choose the best answer, or collate all the answers using some process, and then give it out. So that's distribution for us. So in simple words, distribution is equal to parallelism plus network, because network is the big thing, and there is no shared memory also. Yeah, and the network is where the pain lives, because last week's latency hierarchy we observed that a network hops in orders of magnitude slower than memory. We notice that within the memory, while a transaction could take in 10 milliseconds, over the network it's approximately 100 milliseconds. To the order of 10, it simply multiplies. Yeah, and there is a very brutal law called Amdahl's law. What does it say? Your speed up is capped with a fraction of the work that can be parallelized. So imagine there is 100% parallelization that needs to be done, and of that 50% is sequential. In this, we can speed up to 5x times. If it is 75, 10x times maybe. If it is 10% sequential, 90% parallel, we can go to 15x. But as we go towards more and more machines, there is a limit that we are reaching called 20x, approximately 20x, and beyond that, no amount of machines can break the ceiling. That's what Amdahl's law says. So, even in distributed network, we are gonna hit a ceiling beyond which we cannot improve the performance. And that's what this says. Even if you go to infinity machines, 20x is the limit that you can hit as a ceiling. Yeah. So the cost is linear because we are adding more and more machines. The cost becomes linear. I add 10 machines, maybe it's $10,000. If it is 100 machines, so $10,000 becomes maybe $100,000. And if I had 1,000 machines, another multiplication of 10, which is almost 1 million. So the cost is always linear, but the doubling the cluster rarely doubles the speed, because we are hitting a ceiling here. Yeah, we are not doubling the speed, we are only hitting 20x, and beyond that nothing improves. So our reply in the room as a product manager is, what fraction is actually parallel and what's the ceiling, how much are we hitting? And there are many challenges with doing the distributed compute as well. Yeah, there is partial failure, there is cap, there is consistency issues, and then a different class of problem as well. Yeah, and these are all a different class of problems in themselves. Yeah, cap, consistency, and partial failure. Partial failure is the biggest. Okay, just to be very honest with you all, imagine some nodes fail while others run successfully. Yeah, and we have not tracked them. Yeah, and we don't know whether a node is dead or just slow because it's not performing. So a whole discipline called retries, timeouts, redundancy, yeah, with no single machine equivalent, needs to be built out there. And these themselves take a time, they need a separate architecture and so on. And then there is something called eventual consistency that we could look at. Yeah, the common compromise that we always do is, hey, accept temporary disagreement for availability and speed. Yeah, consistency and availability, you can do that. But for performance, but eventual consistency is what we are looking at. We are saying that, hey, converge eventually after a couple of seconds. uh, when you comment on Instagram or somewhere, your comment shows up quickly for you. but for your friends it takes time because there is eventual consistency that sync that is happening there. Yeah. So the cap theorem says when the network splits, you have to only pick one. You either pick consistency and performance or availability and performance. You cannot pick both. So when you pick consistency and performance, you refuse to answer rather than serve the stale data. Yeah, because availability is not there, so we refuse to answer, and we can since it is consistent, we don't serve stale data, we only just refuse to answer. Yeah. In banking and inventory, whenever there is a query happening to a banking system, the data is always consistent, we cannot say the data is stale there. Yeah. So that's consistency and performance. If you choose availability and performance, that is the system always answers quickly even if the data is stale. That's what happens with social feeds and catalogs. Yeah. System, the data could be a little stale, nobody cares there. Yeah. It's not impacting the business as high as the banking and inventory systems. Yeah. So cap is a product design disguised as engineering, because we as product managers need to take decision. Can we say, hey, can this feature show slightly stale data for a second to stay fast, or it must always stay exactly correct? That's choosing AP versus CP, and it changes the architecture, the cost, the failure behaviors, and everything that's downstream. And that brings us to the important topic of distributed computing. Yeah. Especially distributed AI training. What happens here is we are splitting the work in three ways, and frontier training typically uses all the three at once. Imagine there is data, there is model, and then there is pipeline, all the three that are working. And data parallelism typically says that, hey, you take the data, each GPU holds a full copy of that model and trains a different batch, then syncs back the gradients. Yeah. So the data needs to be split across, and so that this happens, the model fits on one GPU but training is slow. Yeah. So you need to parallelize the same model into multiple systems, use the same data and speed up their training, and then sync the gradients. Yeah. But the challenge here is the communication cost, because all gradients at every step need to be synced together with other gradients from other machines. It's heavy communication cost. Yeah. You can look at data sorry, the model or tensor parallelism. In this, the same model, yeah, one layer's math is split across GPUs, the model is split across multiple machines. Instead of the data being split, here model is being split. So the model is too big to fit on one GPU. We understood that this is a compute problem. So you either increase the machine size or you split the model to work on multiple GPUs. And again here, the constant chatter within each layer is also heaviest, because you're splitting the model across GPUs. Now there are more weights that need to talk to each other. Billions of parameters that need to be updated are spread across these, and since each parameter will depend on hundreds and millions of other parameters, they they have to be synced together, they have to communicate together, they have to be updated at each epoch, and this epochs will be in millions of times. So this is the heaviest of all, because the model is being split and model needs to communicate regularly to update all the weights across its layers. The last one is pipeline parallelism. Here we are saying the layers are being split across. So in a sequence of layers, the layers are being split across. Yeah, this means different GPUs hold different layers, and it's like a factory line. Yeah, it's very applicable for very deep models where there are 20, 30 layers or 40 layers and above. Yeah. And this can be combined with the above, either with data or model parallelism. And how does the communication cost impact? The handoff activations between stages incur the communication cost between us. So it will depend on the two layers that are being split across two GPUs, and how much compute at that stage is required between those two layers. So we need to understand this data parallelism deeply, because it's the most common one. We'll say, hey, there is huge data that needs to be trained. The model could be fit on a single machine. Now the data cannot be run. data is huge to be trained on, and it takes a lot of time. Yeah, because every GPU computes its own gradient, then all GPUs must average their gradients together for every single step, and that sync is the heartbeat of the cost. We need to ensure that when this happens, the time taken to run an epoch does not take forever, and that's only possible when you do data parallelism. Yeah. uh, of the three, the better one is always data parallelism, is how I see it. Yeah. So data parallel training and all the reduce at every step is somehow done like this. Yeah, there is a GPU, there is a full model copy on which there is batch one of data going in, the machine trains and the weights are passed on to another system. Yeah, GPU 2 trains, the weights are passed on, GPU 3 trains, and so on. All these weights are passed on, and then average every GPU's gradients together every single step. Yeah, and this is gigabytes of gradients across the network repeatedly, and this is where the money goes, as in there is a lot of network communication happening in terms of gradient updates, and that network conversation consumes a lot of resources like compute and time and network money. Yeah. So the bottleneck that we are stating is, hey, in large scale scaling, large scale training, GPUs often spend as much time talking to each other as computing past a particular point. Yeah, and past a particular point, more GPUs means so much coordination, you get sublinear speed up. We just noticed that. Yeah, two times the GPUs for 1x the speed, because network limitations, how much GBs can be passed through a particular network is limited. I believe the best networks are today, when between two racks of NVIDIA DGX Spark, I believe the uh, communication gigabit layers are anywhere between 28 to 56 gigabits per second at the best possible network adapters and network cables, and that becomes the bottleneck that explains why cluster economies go at a scale. Yeah, imagine there are specialized interconnect exists. Yeah, this is what I was talking to you. NVLink GPU to GPU and InfiniBand machine to machine. These are ultra fast networks whose whole purpose is to make the talking cheaper. Yeah, and a cluster's interconnect is as strategic as its GPUs, because if they are able to individually do a lot of compute but are not able to share the weights to average it out, the performance will be bottlenecked or the weakest at this interconnect or network. And frontier training cost is what it costs. Yeah, because a large fraction of a run's expense is communication overhead in this case, not raw math. Approximately millions of dollars to train includes GPUs waiting on each other. Yeah, and that's a big cost. So just add GPUs hits two ceilings actually: the sequential fraction, how much can we get out of performance, which is 20x ceiling, and the growing cost, growing sync cost. Yeah, real utilization is often 30 to 50% and not 70 to 80% or 90%. So this is a huge performance metric that we always need to keep in mind when we are talking about purchasing the required cluster sizes for training the machine learning models or your LLM models. Because we expect, or we would do a math saying that, hey, if we do hit 80 to 90% of the machine performance, we would do a training in 2 to 3 days, but ideally it is 30 to 50% only. So we need to always either be wary of how much time it will take, or be wary of how much compute we would need with 30 to 50% of utilization, not 80 to 90%. Yeah. So the build to buy decision that PM needs to take will depend primarily on this communication bottleneck. Yeah, and we need to remember that while training is far more expensive and slower than a naive GPUs in 2 hours. Yeah, the and why frontier training is a game for a handful of players with elite interconnect. That's one very good reason. We need to understand not everybody is able to do. Yeah, that's why in 2026 the rule is rent the model, don't train it. It's very costly to train it. And the drill and the payoff that we need to do anytime we head into a situation where we are saying that, hey, we need to uh, build a distributed system for compute, for memory, and so on. These are some of the questions that we should ideally ask, so that we do not uh, expense at the cost of performance, and which might not be achieved because we have not understood the system properly and we have not asked these forcing questions. Yeah. So the first things that we need to ask is, hey, which forcing function is asking for a distributed system? Is it not able to fit the whole model, or is the system too slow because there is a lot of data? Yeah. If it fits, the model fits, yeah, then you ask for a bigger box, and less data would do. Yeah. Distribution may be premature. Yeah, we need not ask for that. What's the parallelizable fraction and what's the Amdahl ceiling? Yeah, make them state the cap as in the ceiling on that. Infinite GPUs will still only get you 20x the performance improvement, nothing more than that. So that will reframe the whole ambition that we are trying to achieve. And what's the communication cost of the sync? How much communication cost are we looking at between syncing these gradients between machines, and how much data crosses the network per step, how much GB of data is crossing, and what is that interconnects limitations, and where this linear speed up dies. We need to be very clear about that. A real utilization typically is 30 to 50%. A plan assuming 90% is fiction. Yeah, do not budget for this gap, budget for this gap. What breaks on partial failures? When a system silently dies or slows down too much in a cluster or in a distributed system, what breaks immediately? Do we have required checkpoints? Yeah, or do we lose the run? Our one node dies at a R40 of a 2000 GPU run. What happens there? We need to plan for that. Have we compared to renting it, or building a smaller model, or taking an API? Is a very genuine product management question that we need to answer. And for PMs, why does this matter? Because we can challenge that when engineering says just add machines. We need to tell them about the Amdahl law, 20x ceiling, the communication tax return, a tax turn a verb into a number, where we are hitting a hard ceiling and there is a rising coordination cost. Cap, you can't do all consistency, availability, and performance at the same time. You can only choose two. What you choose is a product management decision and not engineering decision. It explains why you rent frontier models, because it's very costlier to build systems that have such high communication tax. So it's easier always to rent these frontier models via APIs and so on. The partial failure changes reliability, because at scale, if you don't know what is breaking, if you have not planned for checkpoints, yeah, in demo it'll work because there is a smaller data, but in production it'll fail. And here are some misconceptions to avoid. More machines means proportionally faster outcomes. No, there is Amdahl law that caps it to 20x, and beyond that, the communication just erodes it. Yeah, the cost stays linear though. Cost keeps rising, the performance has a ceiling limit. Distributed because it's slow. First ask if it fits on one machine, just scale the machine. Consistency and availability, choose one. You cannot choose both. Cost is equal to GPUs into hours into price. That's the cost that we are incurring. So, and utilization also is 30 to 50%, because the rest is all communication. Much of it is communication. Any GPUs wired together is equal to cluster? No, there needs to be an interconnect that is as decisive as the GPUs that we are trying to use. And for interview preparation, here are some 5 questions that we could be asked. Hey, training is slow, let's go distributed. Our response should typically start saying that, hey, what is slow? Is the model fitting on one GPU? If yes, it's just slow. Take a smaller data, improve a better algorithm, slice the data before distribution's complexity, and so on. If we do distribute, I want the parallelizable fraction and the Amdahl ceiling. Yeah, we should be able to hit these ceilings at least. The communication cost of the gradient sync and our expected utilization will always stay at 30 to 50%. and we will always have a checkpoint plan, so that even certain systems die, we are able to recover from that point for further training. Explain the cap theorem to a stakeholder. So we are saying when a network is created between machines, which happens at scale, we can guarantee everyone sees the same data or every request gets an answer, but not both. Because there is certain limitation on the systems. They can either be consistent or they can always be available. We cannot do both, because in large scale systems, when you're trying to write the data, there are multiple actions taking place, and if you want to ensure that every data is initially consistent, you have a single point of write, in which case you can quickly make the system consistent, and availability will take time because you're writing in multiple places and so on. So you can either choose between consistency and availability, but not both at the same time. So CP versus AP becomes very important. Why is frontier training so expensive? Because there is a communication layer in between that, and that is limited, even infinite band, and real utilization is always 30 to 50%. So cost isn't actually GPU into hours into your price, it's much beyond that, and renting is always a cheaper option. Data parallelism versus model parallelism, we looked at it. Data parallelism puts a full model copy on each GPU, and data is split. A different data slice is given, then average gradients are calculated, and when the model fits but training is too slow. Yeah. Model tensor parallelism splits the model itself across GPUs because it's too big to fit on one GPU. The data parallelism syncs once per step, and model parallelism chatters constantly. There is a lot of communication happening between each layer. So it's more communication heavy, and that's why frontier training combines both, plus pipeline parallelism. Yeah. The hardest question that we could ask is, why doesn't doubling the cluster double the speed? Two ceilings. One is the Amdahl's law. Yeah, we are saying the sequential fraction caps total speed up no matter how many machines you add. That's the performance numbers we were calculating earlier. And the communication tags. More GPUs means more gradient sync across the network. So coordination grows even as per GPU work shrinks. Sublinears speed up. Yeah. The cost scales linearly. That's what we saw. While speed flattens, it flattens after a certain point, and the right move may be a better algorithm or a smaller model. And that was track C part 3, that we looked at. We were primarily discussing about, hey, do the systems have enough compute to talk, or are they thinking fast enough? Yeah. And whenever engineering comes with a question of, hey, let's just distribute it, challenge it with the Amdahl plus the communication tags. The communication tags we just looked at, when NVLink or InfiniBand needs to be used, and why realize the actual utilization is always 30 to 50%. Yeah. And that's primarily because there is a lot of coordination happening between the systems. Yeah, that was track C part 3 on distributed and parallel computing.